Welcome. Today we're diving into the fascinating world of Pintle injectors, a key technology in modern liquid rocket engines. Pintle injectors are renowned for their ability to adjust thrust efficiently, making them essential in both lunar missions and reusable rockets. Their unique design allows for precise control over the injection area, which is crucial for variable thrust. In this video, we'll explore how the spray characteristics of these injectors are influenced by upstream flow pulsations, and why understanding these effects is vital for rocket performance and stability. Spray atomization is at the heart of efficient rocket combustion. When liquid propellant is finely atomized, it evaporates and mixes more thoroughly with oxidizer, leading to better combustion and higher thrust. The Pintle injector's spray pattern, droplet size, and breakup process directly influence engine efficiency and stability. Researchers worldwide have focused on understanding these spray characteristics, as even small changes can have significant impacts on rocket performance. Let's see how the Pintle injector stands out in this context. The Pintle injector was first developed at the Jet Propulsion Laboratory and later used in the Apollo program's lunar module descent engine. Its ability to provide a wide range of thrust made it a game-changer for lunar landings. Today, companies like SpaceX continue to use Pintle injectors in their engines, benefiting from their variable thrust and reliable spray characteristics. This legacy highlights the importance of understanding and optimizing Pintle injector performance for future space missions. Simulating the spray from a Pintle injector is no easy task. The breakup of the liquid film, the formation of droplets, and their interactions with high-speed gas flows require advanced numerical methods. In this study, researchers used the volume of fluid (VOF) model and Adaptive Mesh Refinement (AMR) to capture the intricate details of the gas-liquid interface. These techniques allow for accurate tracking of the atomization process, providing insights that are difficult to obtain through experiments alone. The volume of fluid (VOF) model is a powerful tool for simulating multiphase flows. It tracks the volume fraction of each phase, liquid and gas, in every computational cell. This approach naturally handles the breakup and merging of liquid films, making it ideal for studying atomization in Pintle injectors. By solving continuity and momentum equations for both phases, the VOF model provides a detailed picture of how the spray evolves from the injector exit. To accurately capture the fine details of the gas-liquid interface, Adaptive Mesh Refinement (AMR) is used. AMR dynamically refines the computational grid where needed, such as at the interface between liquid and gas, while keeping it coarser elsewhere. This approach ensures high accuracy without excessive computational cost. The octree data structure helps manage these refinements efficiently, enabling the simulation to resolve subtle fluctuations and breakup events in the spray. While the VOF model excels at tracking the liquid-gas interface, analyzing individual droplets requires a different approach. That's where VOF to DPM, discrete phase model conversion, comes in. By identifying near-spherical liquid lumps and converting them into particles, researchers can gather statistics on droplet size, velocity, and distribution. This hybrid method bridges the gap between detailed interface tracking and practical droplet analysis. Let's take a closer look at the Pintle injector's structure. It consists of a central rod, the Pintle, surrounded by an annular gap through which liquid is injected. High-speed gas flows through an outer channel, shearing the liquid film and promoting atomization. The geometry, such as gap thickness, angles, and diameters, plays a crucial role in determining spray characteristics. Understanding these structural details helps explain the observed spray patterns. For the simulations, air and water are used as the primary and secondary phases. The computational domain is carefully defined, using only a quarter of the spray area to save resources. Boundary conditions include constant and pulsating mass flow rates for the liquid, with air treated as an ideal gas. By varying the frequency and amplitude of the liquid's mass flow pulsation, researchers can systematically study their effects on spray characteristics. Before analyzing results, it's crucial to validate the simulation model. The researchers compared their steady spray simulations with experimental and numerical data from previous studies. By refining the mesh and adjusting parameters, they ensured that spray angles and droplet sizes matched reference results within acceptable error margins. This validation builds confidence in the model's ability to predict real-world spray behavior. Under steady flow conditions, the Pintle injector produces a stable, cone-shaped spray. The liquid film breaks up near the injector exit, forming large blocks, filaments, and eventually small droplets. The breakup position remains relatively fixed and the spray angle is consistent. Recirculation zones in the central region help mix droplets, enhancing atomization. This stable pattern is ideal for efficient combustion in rocket engines. When the upstream liquid flow is pulsating, the spray pattern changes dramatically. The breakup position of the liquid film now shifts periodically, and the spray takes on a distinctive Christmas tree shape. This is due to the periodic variation in liquid velocity, which causes faster droplets to catch up with slower ones, creating regions of droplet accumulation. The spray angle remains mostly unchanged, but the spatial distribution and droplet size are strongly affected. By analyzing spray images over one pulsation cycle, researchers observed that the breakup position of the liquid film oscillates in sync with the upstream flow. When the liquid velocity is low, the film breaks up closer to the injector. When velocity is high, the breakup occurs further downstream. This periodic behavior leads to alternating regions of high and low droplet density, which could impact combustion stability in real engines. The frequency of upstream pulsation plays a key role in spray behavior. As the frequency increases, the number of droplet groups rises and their spacing decreases. The spray responds linearly to the pulsation frequency, with each cycle producing a new group of droplets. This means that the atomization process can be finely tuned by adjusting the pulsation frequency, but it also introduces complexity in droplet distribution and potential combustion instabilities. Monitoring the mass flow rate at various cross-sections reveals how pulsation affects droplet movement. Under steady flow, the mass flow rate is uniform across sections. With pulsation, the flow rate oscillates and downstream sections show sharp peaks and valleys, indicating droplet accumulation and dispersion. The phase difference between upstream pulsation and downstream response grows with frequency, affecting the timing and intensity of droplet delivery. Pulsation not only changes the spray pattern but also the size of droplets. Higher pulsation frequencies tend to increase the average droplet size as more droplets cluster together. However, the overall effect of pulsation is to reduce the proportion of large droplets and increase the number of small ones, especially at moderate frequencies. This shift in droplet size distribution can influence combustion efficiency and stability. Visualizing the spatial distribution of droplets shows that the number of bulging structures in the spray increases linearly with pulsation frequency. The central region contains smaller droplets, while larger droplets are found at the periphery. This pattern suggests that internal recirculation helps break up droplets more effectively, enhancing atomization and potentially improving combustion uniformity. The amplitude of upstream pulsation also has a significant impact. At very low amplitudes, the spray pattern is similar to steady flow. As amplitude increases, periodic droplet groups become more pronounced, and the liquid film near the injector exit undergoes stronger deformation. However, the overall spray angle remains nearly constant. High amplitudes can cause the spray to contract toward the center, increasing droplet density and potentially leading to injector tip overheating. At high pulsation amplitudes, the liquid film at the injector exit exhibits a striking contraction-expansion cycle. During contraction, the film is squeezed inward by gas flow. During expansion, it spreads outward as liquid velocity increases. This periodic motion affects the downstream spray pattern, making the Christmas tree effect even more pronounced and influencing droplet distribution in the combustion chamber. Increasing pulsation amplitude generally leads to smaller, more uniformly sized droplets. The solder mean diameter (SMD), mean and median droplet sizes all decrease as amplitude rises. The probability distribution narrows, indicating a more consistent droplet size throughout the spray. This uniformity can be beneficial for combustion, promoting even heat release and reducing pressure differences in the chamber. Summary: the spray characteristics of Pintle injectors are highly sensitive to upstream flow pulsations. Both frequency and amplitude shape the spray pattern, droplet size, and spatial distribution. Understanding these effects is crucial for optimizing rocket engine performance and avoiding issues like combustion instability or injector tip overheating. Advanced simulation tools like VOF and AMR provide valuable insights that guide the design of next-generation rocket injectors.